turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today, the science of paint and where the chemistry stops and art takes over. Us humans have been painting for, according to one source of evidence at least, 164,000 years. From Neanderthals smearing pigments on rocks to intricate masterpieces like the Mona Lisa, most of our focus, though, when we survey a piece of art, is on the brushstrokes, the composition, and what's being depicted. Often we completely overlook the science that underpins the work, and that's what we're going to consider today, how art and science go hand in hand. But how do professional artists approach their work? Well, to sketch out a picture of what's involved, here's Nick Archer, who trained at the Royal Academy of Arts and met me at Queen's College in Cambridge.
I was a student at Leeds. It was a polytechnic then, in the mid-1980s. And I actually studied printmaking because it was seen at the time that art was not really a way to earn a living. Did 10 years working as a specialist decorator and in London, doing rather big glamorous houses in South Kensington, and then applied to do a postgraduate course at the Royal Academy Schools in painting, which is where my heart always was in painting, really. So I went to the Royal Academy Schools 1996 to 1999, where it was quite an academic training, but something that I revelled in and loved as what you would call a mature student at the time.
When you say it was quite academic, in what sense? Were you learning about chemistry and materials at your disposal?
It was quite technical, so there was lots of life drawing, how to draw in an academic way. There was also a lot of colour theory, and that's probably one of the things that I kind of took on board, was all the colour theory.
And what is colour theory? What does that phrase mean?
Colour theory for the artist's use is the optics of colour. We refer to Munsell's colour wheel, which we utilise not only in terms of what the eye wants to see, what the eye will find gratifying in terms of what colour goes next to what colour, but also in terms of how to mix your colour. So, for example, if I have a red and I want to make it slightly less red, I would use the complementary or the opposite of that, such as a bluey green, to make it less saturated and to make it a less bright red. So at first, mixing colour almost felt like a slightly painful activity, but now I've become accustomed to actually really enjoying and loving the process of mixing the colour and discovering how you can get from one colour to another in quite unexpected ways.
What about the different materials you can paint with and the different things you can paint onto? Because art doesn't just start and stop with a pencil or a crayon and a bit of paper.
Sure. I mean, within paints, obviously there are acrylics, there are oil paints, watercolours. A basic rule when using both acrylic and watercolour is you start with the acrylic paint and you can put oil over the top of water-based paints, but not the other way around. But there's nothing quite like oil paint for the richness of the colour. I believe that they can get more particles of pigment in oil than they can in acrylic mediums. So that means that the oil paint tends to be richer in colour, and when I get to the part of the painting where I'm making the colour slightly thicker, I'd often use oil paint just because of the richness of the colour.
Part of the fun, I would think, as a scientist thinking about art, must be the experimentation, that you've got all these opportunities to try different things and try different media. You have on the floor in front of us a stunning piece that you've done. That's actually on a sheet of copper. Talk us through what you've done there and how that came to be. And I love the vibrant colours, by the way. It's beautiful.
Thank you. Yes, I love experimenting with different materials. So I'm fairly standard with the paints I use, acrylic and oil paint. But in terms of the support that I work on, as well as canvas, when I'm working on a smaller scale, I do love working on copper. Copper's quite a traditional surface to work on. It has been done in the past. But I love partly the smooth surface that copper's got, but also the colour of the copper kind of glows through the oil paint somewhat. As I say, the surface of the copper is really quite smooth, so when you apply, in this case, oil paint, I'm able to, with really soft brushes, kind of soften out the brush marks, so you get a really very smooth, almost photographic look to some of the mark making. And what I'm particularly interested with this series of paintings I'm working on at the moment is I'm working from old faded photographs and postcards, some of them Victorian imagery or more up-to-date imagery as well. But I'm interested in how the imagery decomposes and how the imagery fades and how old film or old photographs can kind of disappear over time, and actually some of the blemishes and marks created by the passage of time is as interesting to me as is the original image. So in this painting that we've got on the floor in front of us, I've painted the image in quite a realistic manner, but then I've literally poured and thrown solvent at the painting whilst it's still wet, and it's kind of peeled back and dissolved the paint to kind of reveal the coppery surface underneath. So there's a feeling of the image almost dissolving and disappearing in front of our eyes somewhat.
Is this not a bit high risk, Nick, in the sense that you put 50 hours into making an extraordinarily beautiful painting, then throw some solvent on it to etch out or erode the surface almost in various places? That must go wrong sometimes. Do you not go, oh no, I've ruined it?
Yes, all the time. So it is hit and miss, but that's part of the enjoyment of being a painter. I don't think I'd want to be in a place where I'm just starting a painting and finishing it. For me, there's got to be some happy accident. It may be slightly calculated accident, but some kind of risk involved that kind of gives you a bit of an excitement. So yeah, I paint the image and then I do try randomly just to throw stuff at it to partly destroy the image. Obviously, it does sometimes go too far, or the splash of solvent will land in the wrong place and things will just disappear and it'll become a muddy mess, nothing more really. But I'd say 50-50 work out. The ones that don't work out get recycled and sanded off and I start again basically. But that's, for me, part of the excitement of the process.
And people say science is a high-risk career. His work was absolutely beautiful, though, and you can see for yourself the talents of artist Nick Archer in action on his website at nicholasarcher.com. Now, Nick was just explaining how at art school they taught him to mix colours. But until some of the great scientific luminaries like Isaac Newton and James Clerk Maxwell came along and shed light on the mystery, no one really even knew what colour was or how it worked. Celebrated science writer Phil Ball explored how this field evolved in his book Bright Earth, The Invention of Colour, and he takes up the story.
There are three things that are involved in creating a colour. There's the substance itself, the pigment or the dye, whatever we're using that's coloured. There's the light that transmits the colour from that substance to our eye. And then there's our eye itself, which processes that light. And artists and scientists have wondered for centuries about how all of this works. Isaac Newton was the first person to fully understand that colours are essentially already contained in white sunlight. So when you pass that sunlight through a prism, it splits apart into this coloured spectrum that everyone will be familiar with. Once you've split it into a spectrum, if you take all that coloured light and then send it back using a lens, focus it back together again, you can reconstitute the white light. When this light full of colours falls on an object, some of the colours might be absorbed by that object and the rest are reflected. And it's the ones that are reflected that give rise to the colour. This was all fine, but it didn't seem to correspond to what artists knew, that, this idea that somehow if you mix all the colours you get white. Well, clearly that's not what happens if you do that with paint. You get this kind of murky, horrible brown. That was only clarified in the 19th century when James Clerk Maxwell, Scottish physicist, showed that mixing light is not the same as mixing pigments. If you mix pigments, if you mix, a blue and a yellow to make a green, what each of those pigments is doing is taking out a chunk of the sunlight. So less and less is being reflected. And eventually, if you've got enough pigments mixed up, you're getting something close to black. Nothing is being reflected back.
And if we go back in history, did people chase chemistry to give them art? Or did art lead to some new chemistry? In other words, were people trying actively to make substances, make chemicals, make colours? Or did they go about things industrially and think, well, that's a nice colour, I'll have that, and then work out how to make more of it?
It was a bit of both, but on the whole, it was the latter for most of history, actually. It was trial and error. An example of that was something that happened at the beginning of the 18th century when an alchemist basically was trying to make a particular kind of dye. And he was working in the lab of another alchemist and he wanted to borrow some substance, basically some alkali. And so the other guy gave him this alkali, but it turned out to be contaminated with animal fat. And so when he did his reaction, he didn't get what he thought he was going to get. He got this rich blue substance, and that was because of the organic stuff in this alkali. And this was what became known as Prussian blue, because these experiments were done in Berlin, in what was then Prussia. A lovely sort of rich blue that was much cheaper than the best blue previously, which was ultramarine. So Prussian blue. This alchemist thought, okay, I can market this. And he did that, and he kept the formula secret for a long time, but eventually people worked it out.
When did it stop being ad hoc? We mix a bit of this with a bit of that and turn into things that were very scientifically driven, where people kind of understood the rheology, how paints behave and flow. They understood the chemistry of the colours, how you can mix things together to get the sort of effect they wanted. So you almost rationally design a pigment. Was there a point at which that began to happen, when our scientific nous reached a certain threshold, perhaps?
Yes, there was. It was really in the late 19th century. So in the early part of that century, chemists discovered several new metals that made colored substances, cadmium and chromium in particular. And cadmium colors and chromium colors, they're still used or talked about by artists. But they still didn't really understand the chemistry of what was going on. It was really the dye industry that led to this more rational approach to color. Because in the middle of the 19th century, a new class of dyes was created from substances, organic compounds extracted from coal tar, leftover residue of when you extract gas from oil. This led to an explosion of new colors, of new dyes. So these were dyes rather than pigments. You could use them on clothes, but you couldn't easily use them in paint. You had to figure out how to turn them into a pigment. They were made through chemistry, and it was at a time when chemists were starting to really get to grips with what chemistry was about, atoms in particular, sort of configurations, particular shapes in molecules. And towards the end of the century, because it became big business, some of the big dye manufacturers employed chemists to try to figure out what was going on and also to try to find new dyes. And they started to try to do that rationally by sort of saying, okay, here's the structure of this molecule, here's the color it is. If we tweak that structure a little bit, do we get a different color? That kind of supercharged organic chemistry. There was a lot of discussion about how good they were as colors. Because they're made of organic molecules, they're not very stable. If they're subjected to sunlight, if you leave the dyed material out in the sun, it's going to fade eventually because the sunlight will break apart these carbon-based molecules in a way that doesn't happen if you're making color from metal atoms.
Has that been solved in the more modern era?
Well, it's been solved to a degree, I think, is what we'd say. The organic molecules now that are used in the sort of paints you would go into a shop and buy, they're complex things like quinacridones, and they're pretty stable. So they're going to hang around for an appreciable time. Whether they'll stand the test over centuries, like some of the art of the Renaissance has, that's another matter. One of the astonishing things about Renaissance art, when they were using these inorganic materials made from basically metal compounds, how well they've stood up. You had to know what you were doing. You had to know how to mix your paint, how to apply varnishes and all the rest of it to be sure that those colors would remain vibrant. But some of them have remained incredibly rich. So whether these newer colors will continue to do that still remains to be seen.
Will modern art stand the test of time in more ways than one? That is the question. Phil Ball there, who's the author of Bright Earth, The Invention of Colour.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to the Naked Scientist podcast with me, Chris Smith, and this week we are exploring the science of pigments and paint. In a minute, how you turn back the ravages of time and restore works of art. But first, paint isn't just about colour. If you think about the characteristics of the finish, it can be glossy, satin or matte, and also how the paint goes onto the surface in the first place. It can be thick and gloopy, or it can be thin and runny. So how's that achieved? Here to explain is Narayan Kandekar, who's a conservator and researcher at the Harvard Art Museums.
When you want to make a paint, what you have is a pigment, and that's the coloured material, coloured particles. You need to be able to hold those in place. And what you need to do is mix the pigment with a binding medium. And in the simplest paint, it's just those two components. So in a way, very similar to grinding herbs in your kitchen. You'll put pigment and binding medium together and then grind them together. And what you want is for the binding medium to fully cover each pigment particle.
Is that the same as a solvent?
So a binding medium is different from a solvent. A binding medium does not evaporate, it stays in place. And it's the material that gives you the brushability, the impasto, the drying qualities, the matteness, the glossiness. The solvent dilutes the binding medium. And so what it does is get in there and it makes the paint thinner and makes it more washy as you use the paint.
So in essence then, we've got a sort of holy trinity there, which is we've got something to give colour, which are particles of some description. We've got something to bind them together and give a sort of matrix which they sit in. And then we've got a solvent to make everything flow nicely and give the characteristic to the whatever the paint is. And that solvent then exits the premises later. And that leaves you with the pigment particles embedded in that binder on a surface.
That's exactly right.
And how does one choose then what will go well together in that holy trinity?
There's a lot of trial and error, finding out which pigments work with what binding medium. And there's a lot of binding media to choose from as well. And I could give you a long list, and a lot of them come from the kitchen. So I suspect that people were cleaning their dishes and then going, this is very sticky, it doesn't come off. Maybe this would be a good binding medium. So egg tempera is one of those where you use egg yolk or whole egg, and you mix the pigment with that, and you see that on Italian altarpieces a lot. You have things like animal glue, which is essentially gelatin, and it's the collagen that comes out of bones, hooves, horns, skin. Milk is another one. Proteins from milk, casein, gives you a binding medium that is very durable, and it was used a lot in house paint for interiors in the early part of the 20th century. Waxes, which have been used for thousands of years. So beeswax in, say, Egyptian funerary portraits, or Jasper Johns in the 20th century. And then there are other things that can be added to the binding medium that adjust the characteristics. So you can add a little bit of tree resin diterpenoids, triterpenoids, to adjust the glossness, the thickness, and so on of the binding medium as well.
I had no idea that the ancient Italians were painting with egg. But that's incredible. Anyone that's ever dropped their egg sandwich down their white shirt knows just how well it binds to surfaces, I'll give you that. What about the question of making the paint runnier or thicker? Because in some works of art, you want a nice firm paint that you can impart some kind of texture to, whereas sometimes you want something that will lay flat and cross a surface in a very straight way, in a very even way. How is that achieved?
One way to do it is to adjust the particulate matter versus the binder. And you want a lot more particulate matter. So you can add something that's non-coloured to the paint, like powdered marble or other invisible things, chalk dust, that will give body to the paint. If you want to reduce the amount of binder, what you can do is put the paint out on an absorbent surface like cardboard or blotting paper, and the binder will get drawn into that, and then you've got a lot more particulate versus binder, and that's another way of making thick paint. And this is something that we found with John Singer Sargent. He was using in the Boston Public Library something from seaweed. It's called carrageenan. And just south of Boston, about 25 miles south of Boston, there was a big Irish moss or seaweed processing facility. And what he was doing is taking this stuff that was used to gellify foods and other things, putting it in his paint, and it was working like mayonnaise, I guess. It was, making it more thixotropic, and he was using that to create impasto in his paint.
One thing that I think everyone's noticed, though, is that when you put a paint on at first, it very often looks a very different colour to the way it ends up looking later when it dries. Now, why is that? And also, what sort of steps did artists take to compensate so they knew that it was going to look right once they'd finished this enormous fresco or something like that?
Solvents affect the colour of the paint. So when the solvent evaporates, then you have the pigment and the binder together, and that gives you the colour that you're going to have for the rest of time. So it's really the solvent that is causing the problem. So with emulsion paint, it's water. When you're painting the walls at home in your house, you notice that very clearly. And it's with the water that it causes that effect. So when that goes, or if you're using oil paint and the solvent evaporates, that's really what it is. It's not complicated, but it takes you by surprise. Artists don't just walk up to a canvas and suddenly create a masterpiece. There's a ton of work that goes on ahead of time, lots of studies, lots of detailed working out of getting the colour exactly right. Once they understand the material and they spend their lifetime understanding the materials that they're using, then they create their paintings.
I'm still blown away by the fact that some of the world's great masters were painting with egg yolk. Absolutely fascinating. And around Kandikar there at the Harvard Art Museums. Of course, just like the people who painted them, pieces of art are not immune to the ravages of time. Everything ages. Now, sometimes this can play an intentional part in the evolution of a piece of work, but other times pigments can become dulled, pollution and smoke particles can stick to surfaces and colour the images, and sometimes the worst can happen and things can get scratched and broken. At the Hamilton Kerr Institute at Cambridge University, they specialise in the conservation and recreation of old artworks, where expert conservators and scientists work together to restore paintings to their former glory, staying as close as possible, though, to the original. One of the conservators is Christine Kimbriel.
The first thing we do is usually do imaging, because you can learn an awful lot about paintings just by doing technical imaging. One thing is that you do high resolution photography, so you can really zoom in and look at things even when the painting isn't right in front of you. But we also do things like infrared imaging, where we look at the painting in the infrared spectrum, and there we can see things like carbon. Carbon is often present in underdrawings done with charcoal, for example. So we see through the paint and we might see underdrawing. That was one of the first steps of the painter's process. We also do X-rays of paintings, and that can tell us a lot about denser materials that are present, such as lead-containing paint, lead white or red lead. But it also tells us things about the structure. For example, if you have an old panel painting, it might have lots of worm galleries in it, and you can sometimes see those in X-ray. And then we use UV as well, and UV causes certain materials to fluoresce. For example, if there's an aged natural resin varnish covering and somewhat obscuring a painting because it's so old, it's gone all yellow and brittle, it will fluoresce, usually sort of a bright green colour, and that is an immediate giveaway.
Do you sometimes find that what is lurking underneath is more worth having than what's on the top? And sometimes you end up having a conversation with an owner or someone saying, well, I think we should, quite frankly, scrape off this stuff from the top because that's worth a lot less than what you've got lurking below.
Yes, that absolutely does happen. And we have recently, well, I say in the last 15 years perhaps, adopted a new analytical technique called macro XRF scanning, which is a form of elemental analysis that gives us basically maps, distribution maps of different elements. So, for example, copper or lead or iron, which correlates to different pigments. And what's wonderful about that technique is that it allows us a much better insight into, shall we say, things hiding under the surface. It could be artists' changes, but it could also be later restorations that we can see sit on top of something original. And we very much use that as a guide to sort of discuss whether it would be the right approach to remove some of the paint that's on top.
How far can we actually go with restoring things? If you've got aging effects, is it easy to turn back time and get them looking good, or are there limits?
there are definitely limits. So that's where the ethics of conservation come in. And obviously, we never do anything that the owner of a painting doesn't want us to do. There are things that happen with certain paints. For example, you might have fugitive paints like lake colors, so reds and yellows, that will basically fade. And we don't tend to put those back in, even though we can say probably this dress, which is now sort of very, very pale pink, would have been bright pink initially, but we don't repaint it pink. You might also have the pigment smalt, which is a cobalt glass that tends to go from brilliant blue, and then when it's in oil over time, it deteriorates to a brownish color. So you might have a sky that was blue but is now brownish. We don't repaint it blue, but we do try and basically ascertain what it was and what was there. And these days you can do a lot with digital reconstruction as well.
But have we got better ways now of stopping the aging process? So when you come in and work your magic, are there various treatments that we now understand much better, and we understand what the natural history of the aging effect of that material will be, and therefore you think, well, I'll put this on, A, I can get this off at some point in the future, and B, it should stop some of the aging process that was happening previously and buy this painting more time?
Yes and no. Again, I would say there's more you can do in terms of preventive measures than by actually putting things on the painting. I mean, having said that, the main thing we do is we typically put a varnish on a painting, which is a thin resinous coat that protects it from light to some extent. It protects it from dust, and it protects it to some extent from mechanical damage. We can also put it behind glass. So in its frame, we put a glazing in front that provides even more protection without it being an actual intervention on the painting itself. But the main thing is that we can never completely arrest the ongoing deterioration of organic material. But if we make sure that the painting is in a stable environment that doesn't speed up those forms of deterioration, then we can certainly ensure that it lives for longer and can be enjoyed.
How do you make sure that what you're going to do doesn't do damage? Do you start in an imperceptible little bit in the corner or something to make sure, oops, if I put this on, this is actually not going to have the outcome I expected? How do you safeguard against that?
We have protocols where we obviously start from something that is probably unlikely to do very much at all, and then we very slowly up the stakes. So that might mean using higher concentrations of or slightly more aggressive solvents. So we never just throw something very active at it and hope that it goes well. It's a very carefully timed process.
It's a fascinating job, I should imagine, though. And you think what you're getting to do is to put your brush where some of the most famous painters of all time have put you're literally touching their work, which it must be a bit special for you.
It's a great privilege. It's something that I pinch my arm sometimes, I have to admit. It's also a great responsibility, and every conservator has sleepless nights wondering if they went too far or whether the approach they're taking is really the best and the right one, ethically as well. But it's a job very much worth doing.
So what's the fanciest, most expensive bit of art you've had across your desk, and who painted it?
That might have been the Rembrandt portrait, the National Trust's only Rembrandt portrait, which lives at Buckland Abbey but is currently on tour across the country, which I was lucky enough to clean and restore and do some analysis on to support the attributional discussions that were taking place at the time. And at the end of it, it was confirmed as being a work by Rembrandt, which was very exciting.
Well, that is definitely one to remembrant, I suppose you might say. That was Christine Kimbriel at the Hamilton Kerr Institute. Well, hopefully we've painted a clearer picture for you of the art, history and science of colours and pigments and what we can, can't and won't restore. Thanks very much to Rowan Barclay with us from Lucy Cavendish College over the summer for doing a splendid job putting this week's programme together. Next time, 5 years after COVID started to surge again in the autumn of 2020 and we were all contemplating more lockdowns, many agree that since then, the patterns of other diseases like flu and even the common cold seem to have shifted significantly in the aftermath. Many doctors are saying that they're seeing illnesses that they'd only read about in books before, and anecdotally, people are complaining of being more ill, more often for more time. Now, some invoke the idea of immunity debt caused by not catching anything during lockdowns to account for these observations. Others, on the other hand, speculate that COVID itself might have reprogrammed our immunity or induced a state of immune amnesia. So which is it? We're going to try to get to the bottom of it for you on Tuesday. Meanwhile, thanks to everyone who is continuing to help us with our running costs in this new era of The Naked Scientists. You can do that if you like the programme and want to help us out at nakedscientist.com/donate. And if you don't already do so, do please follow us on LinkedIn, Instagram and X. And do also, if you can, leave us a review wherever you're getting your podcasts. It helps guide other people towards what we hope is an enjoyable and informative programme. The Naked Scientists is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the Naked Scientist team, thanks for listening, and until next time, goodbye.